Okay, cool. All right. Really happy to be here. Thank you everyone for taking the time. I hope that you'll find it interesting and thought-provoking. So what I want to share with you is a bit of thoughts and recipes related to LLM post-training, because this is what I do in my job. So to give you a bit of background, I work at Liquid AI, where we make very small models, and I lead the post-training efforts there. I'm also the author of the LLM Engineering's Handbook, published with Pact, and I contributed to the open source community through blog posts, models, and different tools. So the first question is, what is post-training? So post-training is quite easily defined because it's what happens after pre-training. So when you take the base model and all the different things that you apply to it, the first step of post-training is supervised fine-tuning. Supervised fine-tuning is here to help you transform the base model that is unable to complete the prompts that you send it into an assistant like ChatGPT, where instead of just completing your sentence, it's going to learn to answer your questions and follow your instructions. So this is the first step. To do that, we need a dataset of instructions and answers to train the model on this. Then we have two different techniques. Preference alignment. This is more to make a chat model that is optimized for humans. So here you're going to provide examples of chosen answers and rejected answers to guide the model and steer it in a way where it's going to be a bit better for humans. And finally, we have reinforcement learning to create reasoning models. And here the idea is that you're going to provide questions and you know the answers. So you're going to ask the model to produce the answers, extract the answers, compare with the ground truth, and reward it if it's correct. So this is post-training in a nutshell. I just briefly want to mention fine-tuning because this is also a term that is often used. Here in this presentation, when I talk about post-training, I'm thinking about really general purpose models. So it's made on a large scale with over 1 million samples. This is what we do at Liquid with LFM2 models. And for fine-tuning, it's going to be more task or domain specific. So it will require less data, and it's often to have a precise function, right? Like data extraction, like typo correction, that kind of things. And an idea of when to fine-tune is like these 4 blocks. So you want to fine-tune a model when you want to change the output. It can be the structure of the output, because, for example, you need a very precise structure because it's used in another application. This is a good a good use case for fine-tuning. You can also add superficial knowledge. I mean superficial because you cannot teach an entire language with supervised fine-tuning. You just do not have enough data to do this. But if you want to make the model more knowledgeable about a particular subject, can be like yourself, for example, it's possible to do with fine-tuning. And finally, you might want to use it because ChatGPT or Claude or Gemini are just too costly, or there's too much latency, and that can help you. And when you take a base model or like an open source model, it might help you to increase the output quality as well. So in terms of fine-tuning libraries, those are the 3 that I would recommend. The 3 of them are very good. TRL is probably the most up-to-date. So this is made by Hugging Face, and it has a lot of different algorithms. Then you have Axolotl, which has some additional features like data preprocessing that is really nice. It also has YAML configuration files that you can share. And finally, we have Unstoff, which is very, very efficient for single GPU fine-tuning. And it also has useful utilities, for example, to quantize your models into a smaller one. And finally, we have fine-tuning libraries. Not fine-tuning libraries. We have different types of GPU services, infrastructure that you can use to train your models. First one that I recommend is Google Colab. It's very cheap, it's free. So it's nice for quick experiments, but if you need more compute, you might want to move on to cloud GPUs. It's more scalable. It's still quite cheap to run. And finally, if you have a lot of budget, you can buy your own local GPU, but it rarely makes sense. So let's talk about supervised fine-tuning, which is the first step of the post-training pipeline. So with supervised fine-tuning, this is the kind of instruction data samples that you expect. You have an instruction, you have an optional system. Here you are a helpful assistant. You don't need to have it, but the instruction is what the user asks. So this is very essential. And you have the expected output. So in this case, you see that we provide as context the system prompt and the instruction, but we only train on the output. It means that the model will not be trained on the instruction, only the outputs will be used to compute the loss that is used during training. This is pretty standard, but you could also train on everything for particular use cases. This leads us to a very important question: what is a good dataset? So I like to define it in 3 different properties. The first one is accuracy. You want your data to be very accurate and factual. If you ask for a question, the data should have the right answer and not a hallucinated one. You also have diversity. Diversity is not about a single sample, but about the entirety of the data set. You want it to be representative of the use case that you want to train the model on. If it's a general purpose model, it should have a bit of everything. It should have a bit of math, code, etc. And finally, you have complexity. You do not want to fine-tune the model on tasks that are too trivial, and you don't want to fine-tune it on tasks that are impossible for the model to learn. So you need a kind of compromise to force the model to learn stuff without challenging it to the point where it cannot accomplish the task at all. So to give you an example of diversity, here, each point in this plot represents one sample. And you can see that at the bottom, you have a lot of blue points. So this is the entire data set. And you have a cluster in orange that shows math data. You can see there's a cluster of math data. There's also a cluster of code data. And that shows that there's a low diversity. If you only take the orange sample, you're going to have a very domain-specific data set, but it's not going to be all-encompassing. If you look at the high diversity example at the top, however, you see that the yellow dots are uniformly spread, and that will have a lot more diversity. And you can see that this is taken from real life conversations. So of course, if you have a lot of prompts with users querying your LLM, it's going to be very diverse. Let's see how we can create a SFT dataset. So here, there's a very simple pipeline that you can follow to create an instruction following dataset. So you have an example here of instruction following. Write a detailed review of the movie, The Social Network. And then we have 2 constraints. Your entire response should be in English, first constraint, and all lowercase, second constraint. So this is the kind of stuff that you want to do for instruction following. You want to train the model to precisely follow these constraints. So if you have a list of constraints, you can combine them with prompts you have from, for example, natural conversations. Then you can query an LLM, like ChatGPT, for example, to generate the answers. Then, because you know the constraints, you can run tests to make sure that the model actually followed the constraint in the answers. When they passed, you can keep the data. You can decontaminate them to make sure that you are not training on an evaluation dataset. And finally, you can do a bit of keyword exclusion if you want to remove some content from the dataset. And that is a very strong pipeline to make an excellent instruction following dataset. To give you an example of a SFT dataset that has more than instruction following, here's one that I made a while ago. And here you can see 4 different categories. Instruction following is only 4% of the dataset. You also have code, chat, and math data. And we also have a breakdown of datasets that are used. They're all open source. And this is the kind of distribution you have in the instruction dataset, where it's not just about one thing, it's also about a lot of different categories and a lot of different sources to make sure that the data is very diverse and covers all the possible use cases that a user might need when interacting with your model. In terms of training techniques, I want to mention 3 training techniques. They're basically the same, just variations over the same one. So you have full fine-tuning. Full fine-tuning is when you train all the parameters of your model. You take it, you just train on it. It's very naive. It tends to maximize quality, but it also has a very high VRAM usage. So if you do not have the compute to load everything and train the model, you might want to look at parameter efficient techniques. The most popular one is LoRa. In LoRa, for each module that you target inside of the layers of the network, you're going to add two matrices, A and B. And instead of training the entire network, you freeze it and you only train the small matrices. This will help you to greatly speed up training. It also requires less memory because you don't train the entire network, but just the equivalent of 0.1 or 0.5% of the parameters. But it's still a lot of VRAM, still a lot of memory that you need to be able to load the entire model in the original precision. So what you can do is that you can take the model and quantize it. So instead of using 16-bit for each parameter, you can only use 4-bit. And this is what QLoRa does. So it's a compromise because now you use less memory, but also degrades performance. So I would only recommend it if you don't have any other option. If you have the option, I would recommend LoRa because it's a very good trade-off between quality and compute usage. In terms of training parameters, I just want to highlight a few of them that are very important. The most important one is the learning rate. The learning rate controls the strength of the parameter updates. Every time that you train on a batch of data, this will update the parameters of your model. And this basically controls how strong the update should be. If it's too strong, you're going to be too noisy because the parameters are keep going into one direction than the other. And if it's not strong enough, you are going to very, very slowly train your model, which is not great either. So this is a parameter that you need to optimize, and that's probably the most important one. Another one that is very important is the number of epochs, so number of passes over the entire dataset. This is quite related because if you have a slow learning rate, you will need more epochs to see more data for training. Then you have the batch size, which is the number of samples that you see before the parameter update. If you have a large batch size, you're going to use more memory. If you have a smaller one, you're going to use less memory, but same thing is going to be more noisy. And you also have the maximum length of the inputs that the model can process. This is quite important one because if you have a very small max length, it means that your prompt will be very small. But if you have a very large one, once again, it's going to use a lot of memory. So that's going to be a problem with the compute. And finally, you have two parameters that I would say keep them like this, don't touch them. It's the optimizer and the attention mechanisms. So here we have AdamW. It's the name of the most popular optimizer. I would say, yeah, just keep it like this. And the attention mechanism, flash attention, is the most widespread one. So it's also a very good idea to just stick to the basics here. And when it's training, you're probably going to monitor your experiments. There are a lot of ways to do it. There's Trackio from Hugging Face, there's weights and biases, there's a lot of different tools to do it. And here you're going to see your training loss. So the error that the model makes during training, when you train on one batch of samples, you're going to see the error that the model makes. And this is what this is currently tracking. So when the learning rate is too high, you see a good example here where it slowly converges and then there's a sudden spike. So in this case, it was the learning rate. This is a real example that happened to me. It can be other things when you see a learning rate spike. For example, it could be due to bad data. But in this case, it was learning rate. On the right, you see what expected. So a very smooth curve that goes down slowly. And this is probably a very good learning rate value. All right, we're done with supervised fine-tuning. We can move on to the next training algorithm, which is preference alignment. And preference alignment is a family of technique. In this family, the most popular one is direct preference optimization, or DPO. So this is the one that will cover it, that we'll cover here. There are a lot of other training algorithms, but I would recommend this one first. So same thing for instruction, we had instruction and answers that were expected. And here it's instruction, chosen answer, and rejected answer. So here you can see an example. We're going to steer the model to output words, tokens that are more like the chosen answer and less like the rejected one. So this is an example of it. And to create this kind of data, you want to do a pipeline that is a bit bit more complex than instruction following. So for example, here it's a pipeline that is called ultra feedback. It comes from a paper of the same name. And instead of querying one LLM, we're going to query multiple LLMs. Then we're going to use a judge LLM to score them and give them like a score between 0 and 10, for example. And we're going to only keep the ones with the best scores as chosen answers and the one with the worst scores as rejected answers. Then you can remove duplicates, remove short answers. You can filter out all the samples, but this is kind of the template that you want to use. Only keep the best answers as chosen and the worst ones as rejected. So here's another example of datasets that I've made on the open source side. And this also uses a lot of other open source datasets that were filtered. So for example, I only kept the highly scored chosen answers because you do not want to train on chosen answers that are still very bad. I use some rule-based filtering to remove bad samples that sound not very human in the chosen answers. And this is the kind of work that you do when you create a data set. You really need to read all the samples to make sure that you truly understand the failure mode. You truly understand what's good about the data set, what's bad about the data set, and then you can try to filter it, you can try to improve it, or just reject it entirely. That's also a common outcome. Let's talk a bit more about direct preference optimization. So in this training algorithm, you have the model that you want to train, which is called the policy model, and you have a reference model, which is basically the exact same model, except that you freeze it at the beginning of training. So you have this reference model to give you ideas about how the model would have acted without this new training. So it provides a baseline of the probability of outputting each token. And then you're going to compute the difference. You're going to combine the probabilities that are output by the policy model, the one that you're training, with this baseline to calculate this DPO loss. And the idea here is that you want to increase the probability of outputting chosen answers and decrease the probability of outputting rejected answers. So this is what you do in a loop. By providing all these examples of chosen and rejected answers. In terms of training parameters, here it's pretty much the same. The only one that is different is the beta parameter, and this gives you the importance of the reference model, the baseline. So if it's very high, it means that the model will not move away from the baseline too much. If it's very low, it means that it's going to be a lot more exploratory, and the model can really diverge a lot from the baseline. So this is something that you can play with depending on how much you want to keep the original model for the final one after DPO. And that's it for preference alignment. So we can move on to reinforcement learning. And specifically, the technique that we'll talk about here is GRPO, which is the one that was popularized by DeepSeek R1 at the beginning of the year. So same thing in terms of data format, we now have a different expectation. So we have two different formats here. We have instruction data. This is pretty much like the one that we saw for SFT, except here you can see that in the output, we have think tags. So these think tags are going to contain the chain of thought of the model. And then after the think tags, we're going to output the final answer. So this is commonly done for these models because they need to think before they output the final answer. And this warms up the model to output this specific structure. It learns that it needs to output this kind of structure with think and then final answer. And then we can use the model that has been warmed up on this to use it with reinforcement learning data. And here, the difference is that you have instruction and ground truth. So the ground truth, you will use it to extract the answer from the model's response and compare it with it to make sure that it is aligned, or otherwise it's not rewarded. So for the SFT format, here's an example of how to create reasoning data. You have prompts, you know the real answers because it can be extracted from math textbooks, for example. You're going to query a reasoning model like DeepSeek R1 with chain of thoughts that are outputted because some of the models actually hide their chain of thoughts. So you need to have one that actually really clarify the chain of thoughts. And then you can filter out the wrong answers by extracting it and comparing it, as I mentioned. Then you can do semantic duplication, format checking, etc. But this is a robust pipeline to create this kind of data where you have the chain of thought inside of the answers. To give you an example, here's some work that we've done at Liquid with a really tiny math model. So to do math, usually we use really large model. We decided to take the opposite approach for fun to see what it would give in terms of results. So we used a model with only 350 million parameters to do this. And here you see the exact composition of the instruction dataset and the reinforcement learning dataset that we used. The instruction dataset has a lot of samples. It's a really big one. It has more than 4 million samples. And for reinforcement learning, what we did is that instead of just using these datasets, we checked if the model could actually answer it. So this is very connected to the idea of complexity, the data quality that I mentioned at the beginning of this presentation. You want to challenge the model, but it shouldn't be too hard. And because this is such a tiny model, we didn't want to train it on questions, prompts that it will never be able to answer. So to measure what it can do and filter out the answers, the prompts that are too simple or too difficult, we just generated 10 answers and we checked if it was able to answer it correctly once, twice, or more, because if it's not able to answer correctly at all, it means that it's a bad sample. So for GRPO, this is a bit more advanced, but we still have a policy model. This is a model that we want to train. And we also have a reference model. And the idea here is that you're going to create a bunch of generations, so O1, O2, OG, etc. And then you're going to normalize these rewards, and you're going to use the combination of all these rewards, of all these outcomes to create a reward that is relative. So it assigns advantages based not on the absolute performance of the model, is it able to answer the question, but on the relative performance between all your different responses. And then there's a clipped ratio loss that is used to make sure that the training is stable. And so it means that in GRPO, you have reward functions. It can be another LLM that is used in this reward function, but it can also be some Python code. So here's an example I made for a summarization model with Hugging Face. And the idea is that we want to reward the model if the answer is about 50 characters. So this is a bit of Python code to make sure that the length of the answer corresponds to these 50 characters. And then when we monitor the experiment, we see with this summarization model that on the left, you see the generated completion length. So it goes down. At the beginning, it's at 85, and at the end, it's at 55. So the model learns that it needs to decrease the length of its answers. And this is reflected in the training loss. So previously, we saw a training loss that goes down, but with GRPO, because of the KL divergence loss that is used, it actually goes up. If you have a loss of 0, it means that the model doesn't learn anything, so it's really bad. If it goes up, it means that the model is actually learning something, so it's quite positive. And this is what you want to see with GRPO. And in this case, the final model was able to understand and roughly output answers about 50 characters, which was really nice because it was a tiny model, and that's a successful use case with reinforcement learning. You can apply it to a lot of other domains like math, like instruction following, code, etc. And in general, if the model has been pre-trained and retrained successfully on a very high quality data that contains reasoning traces, it is very successful, and it provides a big boost in terms of performance if it's implemented correctly. All right. That's it for the training algorithm. So I just want to recap everything that we said. So we started with the data. What's good data quality and how to generate data. So this is the first step usually in the post-training pipeline. You see it. You see here that it's a loop. You start with the data, then you go to fine-tuning. Here we talked about SFT, DPO, RL. We could have talked about model merging, which is a nice, clever way to reuse the weights of different models that you've trained and combine them together, for example, by just averaging them to boost performance and robustness. Then you go to evaluation. We didn't talk about it too much, but with evaluation, it concerns automated benchmarks, for example, like MMLU, can be judge models to have rewards, or even human evaluation are able to assess the quality of the model. And this gives you valuable feedback to go back to the data set and tweak the data to make sure that, for example, if you see that your model struggles in math, you probably need to have more math data, higher quality math data. So it's really valuable feedback to go back to the data set, fine-tune your model, evaluate it again, and this is a loop where you iterate until you have a model that matches your expectations and it's the best version of what you can build. So yeah, that's it for me. Are there any questions?
Thank you very much, Maxime. It was a very good presentation. I think we have a question from Uday, right? Yeah.
Yeah. First of all, thank you, Mr. Maxime, for your presentation. It was really nice. My question is going to be about hallucination and the max tokens that the model would process, as you said earlier. I think in the example, it was like around 1,000 to 4,000 tokens, which were usually used in the training process. And does this cause the model to, like, since maybe it's not used to these longer questions or longer sequences of input, does it cause the model to maybe hallucinate more often?
Yeah, it's a very good question, very good point. This is completely correct. If you go outside of this max length, the model will not be able to process the input very efficiently. So at Liquid, we only train on 32K tokens because we want them all to be very good over this context window. If you go above 32K, it's going to start degenerating. So there's something that is related to the training itself, the value that you use for the max length during training. And there's also a component that is connected to the size of the model. If you have a tiny model, it's going to struggle with long context a lot more than a big model. Big models are able to process context a lot more efficiently. And I would also say that there is the context window that model providers publicize. They advertise, they say, oh, you can use 1 million tokens with Gemini, for example. And there's the real efficient token window, because we know that even with 1 million tokens, actually, it is a lot less performant if you max out the context window. The models are better with short context, even when they're very big. So this is also something to take into account.
Okay. And what sort of techniques can we use to maybe, even though we trained the model on like maybe 1 to 4K tokens at max, how can we make it so that the model can give better answers at longer tokens, at longer context as well?
It's a good question. There are a lot of techniques to extend the context window, like yarn, rope, and all the variants of it. But it's still very much a data problem. So context extension is kind of a fix, but it's not addressing the root cause of this issue. So I would not say this is a silver bullet. It needs to be used with high quality, long context data that represents what the users really want to know. For example, very long document and then a bunch of questions. You want to really train the model on this to maximize the performance. This is really the way to get better at it. Yes, Jan. Thank you for the link.
Thank you for your answer again, and it was a really good presentation. Thank you.
Thank you.
Could I send you a link in the chat for the technique Maxime mentioned? If you want to look at it, it's a pretty cool. Yeah, I talked with those guys a few days ago, and we mentioned this again. It's still cool. OpenAI even uses it if they are saying true. Yeah, I think Metin has a question.
Yes, thank you for the presentation. I have a question specifically on DPO. On DPO, before the alignment, we perform normally SFT as a part of training. However, for the case of DPO, we want to train the model with the instructions, and I wanted to ask if masking the instruction part for the training is really efficient, as in some techniques I saw that they are not masking the train instructions on the losses by replacing them with -100 tokens. And so
Yeah.
that's
Yeah, this is correct. Indeed, some do not mask the instructions. In general, you do not get a lot of information from the instruction. You do not get a lot of useful feedback from training on it, which is why it is more efficient not to train on it, because it makes training just faster. And instead of training on the instructions, it means that you can train on more answers, which is why personally I don't do it. I never train on instructions, but yeah, depending on the context, some people want to do it. And I think there was like another component in your question, if I'm correct, or have I answered your question?
Yes, the second component was indeed there. I wanted to ask if while training with DPO, we should add the KL regularization term as well as a divergence error. Some techniques use it, for example, to the log loss, I mean.
This is also something that you can play with. Basically, in your DPO loss, you already are comparing your rewards with the reference model. So it means that there's less need of regularization because it's already baked in the loss function. But then you can basically try and see what works best for you. Yeah, that is like a popular extension of DPO.
Thank you very much.
Length normalization, by the way, is another one that works very, very well. I want to mention it since we're talking about DPO loss because usually chosen answers are longer than rejected ones, and that biases the model into thinking that okay, longer is better. And if you have this length normalization loss added to it, this can balance this and also provide better quality overall because the model is less focused on providing long text and more focused on providing high quality text.
Thank you for the answer. We have one more question, I think. Yeah.
Firstly, thank you for your presentation. Have I missed the part where you explained model merging? Because in the conclusion part, there was writing model merging.
Yeah, I'm sorry. Good question. I don't have it in my slides because I thought it would take too long if I added it. But I can briefly talk about it if you want. So model merging is something that you would do during the post-training. Yes, during the post-training pipeline. For example, with base models, you can merge them together. And when we say merging, there are a lot of different techniques that can be used. I would recommend the library called MergeKit if you want to try it. And this is often a good idea to do because when you have a bunch of checkpoints, especially when they train on different data, combining them together, for example, with a simple averaging of the weights, works really well in practice. So you could do it with a base model, you could do it with the instruct model, and you can also do it with the chat model and reasoning model. So basically at every step, you can merge different checkpoints together, and you can be even more creative. And for example, if you have a chat model and a reasoning model, you could try merging them together and the result should be a model that sometimes reasons, sometimes not. It's not very reliable. So I would probably advise to train it again after the merging to make sure that you didn't break anything and that it's behaving as expected. But it's a very popular technique that is now used in every AI lab. So definitely something that you want to check out. But it's not very complex. Model merging doesn't have like a ton of depth. It's a very simple technique that provides a boost of performance overall.
All right, thanks.
By the way, I sent the link for model merge kit. You can look at it as well. Or should I? Yeah.
Hi, Maxime. Thanks. First of all, thank you for your presentation. I want to ask that, like, as you know, when there was OpenLLM leaderboard, like techniques like slope or model stock were very popular. But since the OpenLLM leaderboard has closed, like the popularity of these techniques has decreased. I want to ask that, like, as you know, there are new techniques like Alka fusion or like lots of techniques or evolutionary marking techniques. Like in industry, what kind of techniques do you use most? I want to ask that.
Yeah, I can spill the beans if you want. This is a good question. Yeah, model merging was used in the open source community because it's a very cheap technique. I didn't mention it, but you only need CPU, not GPU. So anybody could do it with Google Colab, and you can easily game a benchmark by merging again and again and again because yeah, this works like this. You can have a bit of contamination, and this goes up like this. So it was very popular during the OpenLLM leaderboard times. It is used in the industry by every lab I know, and usually what is used is the very simple model soup. So model soup is just averaging the weights. Meta released a paper a few days ago about how they do this model soup. It's called LLM souping or something like this, to find the link. And they try to see which models are not correlated with each other and which ones are also the best in some category of a benchmark. And that helps them to design weight factors to do a linear combination of all these models. So it's very, very simple. They're just taking the best model at one thing, combine them with the best model at another thing, etc., etc. And usually this is how it's used in the industry because linear averaging is very robust. It's not biased as the other techniques. So this is the most common one. And then depending on the task, depending on the lab, you can also see other techniques that are used. At Liquid, we like kind of running all of them and then see which one provides the best performance because it's so cheap that you can easily do it at scale. The main cost is actually evaluation because evaluation does require a GPU.
Okay, thank you.
Thank you for the link.
Yeah, by the way, I sent, I think it's the correct link, right, Maxime? Supermodel from Meta.
Yes.
Yeah, okay. Everyone can check this out too. Okay. If you don't have any questions, I think we can end this session. That it was very good presentation. Thank you very much, Maxime, for accepting my invitation. So, yeah.
Yeah.
You want to add something?
Thank you for having me. Thank you for all the questions, and good luck with your post-training endeavors in the future.
Thank you very much.
Thank you.
Good night.
Bye-bye.
Bye.
Good night.